We are group number 10, and we are going to be solving problem number 2. Within the problem, there is a fruit computer company that has requirements for the amount of quality of chips, excellent chips, good chips, and mediocre chips. Their first requirement is that there are 5,000 excellent chips, 3,000 good chips, and 1,000 mediocre. So this quantity would be the quantity of quality of chips. There is a $10 penalty for each excellent chip that does not meet their requirements that was listed above. And that goes the same for the good mediocre chips as well. So $6 of a penalty for the good chips that aren't met, and a $4 penalty for the mediocre chips that are not met. So this is the penalty cost per chip that does not meet the requirements. Additionally, there is another penalty for each dollar that exceeds the budget. So for every dollar that goes over our budget of $28,000, there would be a $1 penalty. Going back up, the problem did say that the fruit company has budgeted $28,000 to spend on all of the chips. So I'm just going to write that there. 28,000 is the annual budget that we cannot exceed. With this problem, there's also a priority as to what the company would like to reach. So within the problem, it says that the highest priority will be not going over that budget constraint. So that's priority number 1. And then the following priorities will be going for just the restrictions of the amount of excellent chips needed. So the 5,000, 3,000, $1,000 amount of chips. So this is the order of priority for this problem. Going into solving our linear program problem, we're going to define the variables. So x1 will represent supplier 1, x2 supplier 2, and x3 supplier 3. And each supplier is going to be supplying 100 lots of chips with varying chip quality, as shown in this table. So just make a note of that. Right. Along with those variables, we have our deviational variables. This IF will represent each goal, so that we have our 4 goals based off our 4 priorities. And we have this one with a little negative on top and one of a positive. So the one of the negative will be representing us coming underneath the IF goal, and the plus would be us exceeding the goal amount. And with there being 4 priorities and 4 goals, we're going to have I go from 1 to 4.
Define the objective, minimize the Pentel associated with the meeting the chips requirements. Minimize the equal 10 is 1 minus plus 6 is 1 is 2 minus plus 4 is 3 minus plus is 4 plus z here it's like total cost of Pentels, and the 10 is 1 plus 6 is 2 plus 4 is 3. Pentel cost per chips that does not meet requirements is for Pentel cost for exceeding no no budget. The coefficient in front of the division variables represent the Pentel pair constraint. Divine constraint. One here 60x1 plus 50x2 plus 40x3 plus s1 minus s1 plus equal 5000, which is excellent chips. And here the second 20x1 plus 35x2 plus 20x3 plus s2 minus s2 minus equal 3000, which is good chips. The third one 20x1 plus 15x2 plus 40 x3 plus s3 minus s3 minus equal 1000. Score chips. 400x1 plus 300x2 plus 250x3 plus s4 minus s4 plus equal 2800. Budget constraint. The sign restriction x1 comma x2 x3 and greater than 0. S1 minus S2 S3 S4 greater than 0. S1 S2 S3 S4 greater than 0. Non negative.
All right, so our final summary of the equation for our fruit computer company. Our total goal is to minimize Z, which would be minimizing our total budget. So we get the formula min Z equals 10 S1 minus plus 6 S2 minus plus 4 S3 minus plus S4 plus, such that our constraint number one is 60x1 plus 50x2 plus 40x3 plus s1 minus s1 plus equals 5000 for our excellent chips. Constraint number two would be 20x1 plus 35x2 plus 20x3 plus s2 minus s2 minus equals 3000 for our good chips, s2 plus, excuse me. Constraint number three would be 20x1 plus 15x2 plus 40x3 plus s3 minus s3 plus equals 1000 chips for our mediocre chips. And then our final constraint is our budget constraint. That's going to be 400x1 plus 300x2 plus 250x3 plus S4 minus S4 plus of a budget of $28,000. With our non-negativity constraints being x1, x2, and x3 greater than or equal to 0. S1 minus, S2 minus, S3 minus, and S4 minus greater than or equal to 0. And then S1 plus, S2 plus, S3 plus, and S4 plus greater than or equal to 0. We ended up plugging into CFlex to find our solution. So our first solution is going to be for our weighted penalty. This is going to be your best total cost plan. So in the equation, we label out how many integers. So we have how many suppliers. We have 3 suppliers. We created a range. We're going from 1 to suppliers, which is 1 to 3. We have our variables, which are floats. We entered the table in there with excellent being 60, 50, and 40, good being 20, 35, 20, mediocre being 20, 15, 40, and then cost being 400, 300, and 250. That was based off of table 57. And then our needs. So we need 5,000 for excellent. We need 3,000 chips for good chips. We need 1,000 mediocre chips at a budget of 28,000. And then according to our final or to our objective function, the next part is our summary. So we have S1 minus, S2 minus, S3 minus, and S4 minus for our variables with X in there as well. And then our program, so we're minimizing the 10 times S1 minus plus 6 times S2 minus plus 4 times S3 minus plus S4 plus. So once again, that was our objective function. And then we found the sum down here at the bottom. And our final answer for this one is the best overall total cost plan would be to buy 100 sets of chips, 100 lots of chips from supplier 2 for excellent, good, and mediocre at a cost of $30,000 total. So we are $2,000 over budget. So that is the optimal solution if we're just finding just the one, the single objective. Now the next coding, this is weighing our preemptive goal plan. So the coding didn't really change, except at the bottom we have minimize static LEX, static LEX, which that just shows us getting the budget, or the preemptive goal planning, showing the priorities. So S4 plus is our priority 1, and then S1 minus, or S4 plus being our budget. S1 minus is our excellent, and then S2 minus is good, and then S3 minus is mediocre. Those are the order of our priorities. When we run that, our solution is our optimal option to hit our priority 1, which is our budget, is to be 333.33, or rounding 333 chips short of our excellent chips. So we end up with 4,667 chips, but we will meet with the surplus our good chips and our mediocre chips, and that hits us right at $28,000 for our budget. We're not overspending on this one. So depending on which is the most optimal, so if you look at the numbers, our most optimal to have the least amount of penalty would be our weighted LP, the single objective up top, which would be buying 100 chips from supplier 2 and only being $2,000 over budget. So that is our solution for problem number 2 for this project. So we appreciate your time. Thank you very much.